Hi, everybody. I hope you're doing well. Today, we're going to continue talking about the quantum mechanics of three-dimensional systems. And today, in particular, we're going to focus on systems that have spherical symmetry. These are called central force problems. And the most famous of this, or the most important for us, is the hydrogen atom, which we'll get to next time. Okay? But today, we're going to just introduce the problem and show some interesting features of central force systems. And one is that angular momentum is conserved. So angular momentum is going to become an important player. Well, hang on. We're going to take a look at the notebook to start going through this. Okay, so last time we introduced three-dimensional quantum systems. We found that in 3 dimensions, the wave function is a function of position in 3 dimensions. I guess that makes sense. So in Cartesian coordinates, we might write it as psi of x, y, and z. And Schrodinger's equation also looks different in 3-dimensional systems. We wrote it this way: minus h bar squared over 2m times the second times the second spatial derivative of psi, which we write in 3 dimensions as del squared psi. And this has to be equal to E minus U of R, potential energy is a function of position, times psi. Okay? And here, the del squared operator has a specific meaning. It's the second spatial derivative. And if we write it out in Cartesian coordinates, it looks like this: second derivative with respect to x plus second derivative with respect to y plus second derivative with respect to z. And then in this case, it's acting on psi. Okay? Last time we did an example, which was the particle in a 3-dimensional box. And in our case, we chose a box that had dimensions of L by L by L. I'll just draw it as a square here, but we had a 3-dimensional cube. And we found the wave functions and the energies for this. And in particular, I'll just write down the energies here. We found the energy depended on 3 quantum numbers, okay? And we could write this as h squared over 8m L squared, that's certainly familiar looking, times nx squared plus ny squared plus nz squared. So 3 different quantum numbers for this 3-dimensional system, okay? And we found the energies exhibited some interesting features. One was degeneracy, that we can have more than one state with the same energy. For example, the state with nx equals 2, ny equals 1, and z equals 1 has the same energy as the state with nx equals 1, and y equals 2, and z equals 1, and so on. Now, in this case, the system that we examined had Cartesian symmetry, okay, rectangular symmetry. But the cases we're going to talk about now will have spherical symmetry. And as I mentioned, these are called central force systems. Okay? What I mean by that is the following: the potential energy, which in principle depends on all 3 coordinates, x, y, and z, here is only going to depend on the distance from the origin. And if you think about it, that means that the potential will be spherically symmetric, because it'll depend on distance to the origin, but not on any angles or direction. And you can also imagine that the hydrogen atom, for example, is such a problem because the potential that the electron feels in the vicinity of the proton depends only on the distance between the electron and the proton, but not on direction. Okay? So that's the system that we're going to investigate. So these problems have spherical symmetry. And they also have a special property, which is that in such systems, angular momentum is conserved because there are no tangential forces to exert a torque on the system to change the angular momentum. Finally, I suppose it makes sense, but systems like these are best treated in spherical polar coordinates. Okay? And I know these coordinates are familiar to everyone, but let's just quickly review it so that we're all on the same page. So in spherical polar coordinates, we replace x, y, and z, the Cartesian coordinates, by r, theta, and phi. And these are defined in the following way. Give me a second to make this sketch that you're probably familiar with. If I draw Cartesian coordinate system here, and label, well, let's see, we have x, y, and z. And if we have some point here, then in spherical polar coordinates, r is the distance from the origin out to the point. Theta is the polar angle. It's measured down from the z-axis. And then if we drop a line perpendicular to the xy plane down until it intersects the xy plane, and draw a line out from the origin to that intersection point, the angle that makes with the x-axis is the phi angle. So we have r, the distance to the origin, theta, which is called the polar angle, and phi, which is the tangential angle or azimuthal angle. And it's easy to work out the relationship between x, y, and z. Z turns out to be equal to r times cosine theta. X turns out to be r times sine theta times cosine phi. And y turns out to be r sine theta sine phi. Okay? Where, of course, r is just given by x squared plus y squared plus z squared. Okay? So, spherical polar coordinates. Yes. Now, the next task we have isn't an easy one. So, in keeping with the spirit of this course, we're actually not going to go through the details. The next task we have is to write out Schrodinger's equation, but in spherical polar coordinates instead of Cartesian coordinates. Okay? Okay. Now, the meaning of the equation doesn't change. It's just the way that it's expressed that has to change. And here's the rub. This term, del squared psi, which we wrote a moment ago in the following way, in Cartesian coordinates, looks quite different in spherical polar coordinates. And it's a little uglier, okay? And here I'll write it out. And I don't mean for you to memorize this. I just want you to see that this can be done with a little bit of algebra, and we can find the solution. And here's what it looks like in spherical polar coordinates. Second derivative with respect to r plus 2 over r, first derivative with respect to r, plus 1 over r squared times second derivative with respect to theta, plus cotangent of theta times the first derivative with respect to theta. I'm not sure I'm going to fit everything on this line, plus cosecant squared of theta times second derivative with respect to phi. All of that acting on the wave function. Okay, oh, I need to close that parenthesis there. So it looks a little bit uglier, okay? But really, it's not the end of the world. So we're going to see how we can work with Schrodinger's equation in spherical polar coordinates and how we can break it up into something simpler looking for central force potentials. All right.